Okay.
Okay, so it's an update on the Onyx SIG compiler. So you probably know there are multiple LLVM-based compiler. IRE is one, TorchMLIR is another one, and we a third one which is owned by Onyx, which is Onyx MLIR. And so the compiler SIG groups focus mostly on the development and the maintenance of Onyx MLIR. In general, we have last year we had about 15 active contributors, and historically we have had more than 100. But I think in general, so we have a bit fewer than in the past. It's pretty active. On average, we have 350 PR every year, and our focus is on optimized code generation, support for newer Onyx operations, and also accelerator support. So the ecosystem is that we based on MLR toolchain, and MLR stands for multi-level intermediate representation. And in general, so we include basically MLIR whenever MLR is upgraded. So we update it into our own repo, and it's usually bi-monthly, but sometimes a little bit slower. And we do it typically in sync with other MLIR dependent projects, tool chains. So the architecture is as shown here. So the input is an Onyx model, and then we go into the Onyx MLIR compiler. It's a compiler, but it's really faithful to the MLIR standards in the sense that we do lowering bit by bit. So in red, this is what we do at IBM. But in general, so the target of the compiler can either be LLVM-IR, which is basically going to be then going to binary. But you can also have an Onyx output, so Onyx MLI dialect, or you can have TOSA, and that's other people working on it, or stable HLO. And so those are current options that are available. So, and the idea is that some folks, for example, other companies have their pipeline already optimized for TOSA. That means that they generate code for their GPUs and they have invested a lot in the TOSA. So if they wanted to inject Onyx, they basically can go this path to get their lowering. Because we go through LLVM, so obviously we can target, and the LLVM compiler is very, can target large numbers of machines. So obviously it runs on lots of different machines. We test it on our own machine, Power, x86, and ARM. So those are the platforms we have in our CIs. And so if you talk about our executable binaries, we have binding basically on how to make inference both in Python, C, C++, and Java, so that you can perform, basically use this model. And for us, the output is basically a .so, or like basically a binary that you can load into your application. So it's a little bit like an edge thing where your entire model is embedded and compiled down to an executable, as if you had a C++ program that you compiled. So I'm just going to give you just two optimizations. So that's some of the ones that we worked recently, but obviously it's a small subset of everything that we do. So we typically using accelerators like in our environment. And so those are on the Z Telum, we have the AI integrated AI accelerator. But however, so they're very good at doing a matrix multiply, convolution, and this kind of stuff. But if you look even at a model like an LLM, there's still a lot of operations where you have to transform, you transpose. And for us also, when you go back and forth between the CPU and the accelerator, we have different number representation, FP16 versus FP32. So we have also to do some conversions. So we put a lot of effort on the compiler optimization, try to remove those overhead or lower those overhead on CPU. And that's as an example here. It's very specific to us, but in general, I mean, I think that's something that you probably would see in other places. In blue, those are operation that works on the accelerator. And so in red sort of things, or red or orange, I think so on the CPU. And in this case, we have something that we call unstick, where you have to change the data layout because basically the layout for accelerator is different than the layout on CPU. And then there's also, like in this case, there's a transpose operation that needs to be done. And then we need to put back the data in the format that accelerator wants. And so so we decompose this transformation from between the data layout and so the data format as a tiling operation, and then as a data conversions from 16 to 32 and 32 to 16. And obviously, we can, since when transpose is just moving data around, so we don't need to operate on them. So we can just omit those things. And then we're going to do tile aware, basically transpose, where we taught the compiler when where to get the data in the tiled version. So it's just a mapping. So we taught it how to read and write the data in this tiled format, and we apply the transpose. And so originally we had 3 loops with 5 data streams, and we get down to 1 loop with 1 load and 1 store. So basically that goes faster. And so here I have on the right-hand side, Granite results. Granite is like basically an LLM built by IBM, but based on Llama. And so it decreased the number of, just this operation, about 26% of those overheads of moving data around. And, this is just an example where we do a lot of similar things. Sometimes also we operate on data. So if you just have to add or operation that not supported in it, we can do on the fly data transform and operate on data in FP32 and then convert it back if need to be converted back. And another one is exploit parallelism. So we have parallelism both on the CPU and also in the number of accelerators that we have. And so we use OpenMP parallels to invoke multiple accelerators and CPU. And we also use quantization for selected matrix multiply. And all this is driven by the compiler. So in this case, it's again a Granite model. And so we started, with a fairly long latency, and then we started using ZIU is what we call our accelerator. So we have multiple accelerators, and then we use multiple CPUs and multiple accelerators because there's different tasks that they do, and then we add quantization. And so in this case, that was 6x faster from the beginning of using the accelerator to once we optimize. So that's this kind of work that the compiler does for you, and obviously make us go faster. So we encourage new users and developers to join in. Our Onyx ML can be used in a very modular fashion because you can basically come from the Onyx protobuf, the Onyx model, and then you can exit at various different levels where it's good for you. And via the backend, obviously, we can generate code like CPU code for various different, and we try to optimize, many of those operations. Our target is typically this accelerator, but we also spend some time accelerating things that would go on the accelerator, but we can also execute on CPU. But specifically, our accelerator support is fairly generic. So you could come with a different accelerator and add it. And so some of the next ongoing steps, we support for new LLM related operations that we're very happy that have been added because I think that'll make Onyx in general more useful for our clients. We have a PyTorch integrations where basically we run our Onyx models. We have a Torch backend where we translate to Onyx and then we run our compiler and we can cache in the models and so the first time is slow and then it goes faster. And so we find that often clients sometimes they want to quickly experiment if something works, that they don't want to change their entire code to go to a different framework, so they can experiment within that model. So that's useful to them. And also, so what we discovered now, we started using also more and more AI. So basically the compiler was developed by humans for humans, but we find that sometimes we can simplify or we can make AI more successful by changing a little bit how you write the compiler code in a slightly more systematic way that maybe is a little bit more verbose, but that is easier to generate. So that's some of the effort that we're trying to do to make our life easier and to use more successfully coding agents. That's it. Thank you.
Thanks. Any questions, comments?
The PyTorch integration.
Yep.
saves it into an intermediate cache state. So it's
Yeah.
not Onyx per se, it's just like an Onyx MLIR.
No, we literally translate in an Onyx model.
Oh, okay, so the PyTorch integration is PyTorch, Onyx, and then Onyx to Onyx MLIR.
Exactly. Yeah.
Okay, so it's not a separate path. Okay.
No, exactly. We're reusing everything. So basically, we
Okay.
use the automatic translator, and often models get to split in 6 or 10 models depending on the path and stuff like this. And so then we cache those, and then we can to find out that 2 models are the same is really quick. So then we can just reuse that cached version.
Okay.
Thank you.
So quick comment. You mentioned a Granite model. Is that so? How do you get the Onyx version of the model?
So those for those, I mean, they cached also on the Hugging Face, for example. So we had to manually generate them the first time.
Okay. Okay. All right.
Yeah. And those are in one piece. So basically, we have one piece that does the same thing.
Questions about the runtime of the compiler for models of like certain billion to, I guess, 10 to 20 billions. Does that affect compilation time? What's the typical compilation time that you can see?
Yeah, so I'll be honest. I mean, our machines are not GPUs, so it is still a server. So it is not really meant to compete with GPUs. So we're not super competitive on such large model because all the data compared to a GPU is still coming through we attach basically to the L2 caches, L3 caches. So everything goes through the normal, normal CPU hierarchy. They're pretty high bandwidth, but they're not as good as, distributed GPUs. So we tend to maybe plateau at 8 million model. Okay. And we've done quite a bit of work to try to, as you were saying, to touch the data, we do something similar in our compiler. So basically, when we do constant propagation, we don't actually do the computation. We delay it until all the way we generate values. But it can still be slow. Yeah, it can be slow. So I think maybe it's maybe up to an hour compilation.
What do you see as the bottleneck? Which part would take longer?
I think it's often, handling the data is a significant amount because we go through then eventually LLVM, and we try to also to optimize through LLVM. So that also takes time.
I see.
Yeah.
Thanks.
And the other thing is like, I mean, we've never really invested, but I think if we wanted to really to push it, I mean, we treat basically every operation as a new operation for which we generate code. Technically, you could make functions where you reuse, in different contexts. So that would be a way, because often you have multiple layers, but that's not something that we've tried. I think you could extrapolate that 2 layers the same and making a function and compile it only once.
Yes.
But that's not something that we've looked into.
Okay. Thanks.
Yeah.
Okay. Thanks. If
You're welcome.
there's nothing